we've looked at harmonic motion. In this section, we're going to look at damped harmonic motion. Now, what damped harmonic motion is it's when we've got an oscillator, but it's reducing due to an external force. Okay? So instead of the spring going up and down and up and down and continuing at the same motion, it's going to reduce over time. That's damped harmonic motion. So examples include a swinging pendulum, a weight on a spring, also a resistor inductor, if you know what that is. So damped harmonic motions, there's the formula for that is D of T is equal to A e to the negative ct times cosine or sine of omega t. Okay, so in this formula, A is the displacement of the object. So just like before, it's how far if it's a spring, it's how far it's pulled away. C is a constant called the damping factor. So that's something that will be given in the problem. Omega is related to the period and the frequency, just like before. The period is equal to 2 pi over omega, or omega is equal to 2 pi times the frequency, or the frequency is 1 over the period. The displacement, for example 1, it says the displacement in inches of an object oscillating under damped harmonic motion at time t is given by D equals 10 times E, and that's our number E, okay? 10 times E to the negative 1.4 t times cosine of 3 pi t. It asks us to identify the displacement, the damping factor, and the period. So let's go back and rewrite this on this page. We've got D equals 10 e to the negative 1.4 t cosine of 3 pi times t. Let's, with this, write down our general formula. It's AE to the negative CT times cosine of omega t. So that gives us an idea of where things match up. So the displacement, A, is just 10 inches. The damping factor that's C, and where is C on here? Up there, negative 1.4, or actually just 1.4. We don't need the negative with it because the negative stays anyway. And last, it asks for our period. The period is 2 pi over omega, and omega is 3 pi. So the period is 2/3. Okay, so now we've looked at an example of how to pick out each factor here. The next example we're going to do is actually graphing this and talking about what's happening. There's another formula for damped harmonic motion. I'm not going to do an example with this. I don't think you'll have it on your note, on your exercises, but I'm giving it to you just in case you run into it. Example 2, going back to the original damped formula, it says analyze the damped vibration curve. D of t equals e to the negative t over pi times cosine of t. Okay, so the first thing we'll talk about is finding our restrictions. So our restriction is the absolute value of d of t. So we're taking the absolute value of our function. It's kind of hard to do all together, so we're going to split it up. It's the absolute value of e to the t over pi times the absolute value of cosine of t. It's the same thing. Now, cosine of t is always going to be less than or equal to 1, but it's got to be positive. So, for our situation, so that means that we can take out the cosine of t because it's going to be positive. We don't have to worry about it because we're just talking about absolute value. And this is then less than or equal to e to the negative t divided by pi. And the absolute value of that is just e to the negative t divided by pi. Okay. What did this tell us? This tells us that the function, the displacement, has to be between negative e to the t divided by pi and positive e to the t divided by pi. Well, what is e to the negative t divided by pi? Well, it's whatever we plug in for t. It's a function. We're going to be graphing this thing. So let's go ahead and graph, just so we'll see what this looks like. E to the negative t divided by pi. Well, if we plug in 0 for t, so 0 divided by pi is 0, that's e to the negative 0, or is e to the 0, which is 1. Then we plug in pi over 2. So negative, or is it pi over 2 divided by pi? Take e and raise it. That's e to the negative 1/2. And we're going to need a decimal for that. Then plugging in pi, you get e to the negative 1. Plugging in pi over 2, we get e to the negative 3/2. And 2 pi, we get e to the negative 2. Let me see what I've got over here. Yeah. So I need to grab my calculator and put these in because I didn't do that before. Okay, got them. So e to the negative 1/2 is 0.61. E to the negative 1 is 0.37. E to the negative 3/2 is 0.22. And e to the negative 2 is 0.14. So I'm going to go over here and graph these. Maybe. Okay, so first we've got the point 0, 1. So right there. Then we've got the point pi over 2, 0.61. So something like that. Pi 0.37. See, I think that's supposed to be a 3 pi over 2 up here. There we go. Have to fix that later. But same thing. So 3 pi over 2, 0.22. And 2 pi, 0.14. So what we have is this. And then to graph negative e to the negative t over pi, we just flip it over the x-axis. So what we've got here kind of looks like a funnel of sorts, which makes sense because we're damping where this motion is reducing over time. So it's kind of reducing by these parameters of this funnel. Okay, back. We've got also this cosine to deal with. So we're going to also graph our cosine curve. What we're actually doing here is, and I'm just plugging in these values here and solving, we are combining these two equations to get these two functions together. And we'll talk more about combining waves in the next section. So once we get to the next section, this will be easy because we've already done it. So I'm going to go ahead and graph y equals cosine of t on here. So we've got 0, 1, pi over 2, 0, pi negative 1, 3 pi over 2, 0, and 2 pi 1. So it looks like this. Okay, so we're taking these two and we're combining them together to get the last function. So when you take these values and you multiply them, so basically 1 times 1 is 1. 0.61 times 0 is 0. 0.37 times negative 1 is negative 0.37. 0.22 times 0 is 0. And 0.14 times 1 is 0.14. And now we're going to come and graph that. And watch what happens. So 0, 1, we're graphing, these are our x values, okay, still. So 0, 1. Then we have pi over 2, 0. Then we've got pi negative 0.37. That's down here on that point. And then 3 pi over 2 is back at 0. And then at 2 pi, we're at positive 0.14. So let's see if I can draw this. it's like this. So what you can see here is that purple is in between the blue, but it's combined with the pink, bringing it down in between the blue. And so that's what the damped curve looks like. And that's all we need to do for this section.